Now then, let's try the same exact thing for cosine. So we're going to find the Maclaurin series centered at 0, of course, for cosine x. How do we start? We start by taking a bunch of derivatives. So starting with our original function, cosine x, and take its derivative. And just like with sine, they're going to start repeating, of course. So whoops, what's the negative sign? The second derivative, negative cosine, third, put a 3 there. Let's see, derivative of negative cosine, it's negative sine, so sine. And then we are back to cosine again, and it's just going to repeat over and over. It's cyclical. All right, now what do? You evaluate your function and your derivatives at your center point, and our center point, of course, is 0. It's Maclaurin. So f of 0, what is the cosine of 0? Cosine of 0 starts up in the air, that's 1. And f prime of 0, we got sine, well, sine's going to be 0. This is that negative 0 business. F double prime. Oh, we're back to cosine, but this time it's negative, so that'll be a negative 1. You see what's happening here? Looks sort of familiar. And then here we've got sine again. It's to 0. And the fourth derivative, evaluated at 0, cosine of 0 is back to 1. So we went back to where we started, so we can see that we're going to just duplicate this pattern. The next one's 0, then a negative 1, then a 0, then a positive 1. You get the picture. Okay, now what? Now we fit the little description, the little recipe for the Taylor series, and then see if we can find a pattern amongst all the terms. So our f of x, our function, is going to be represented by this Taylor series as, well, Maclaurin, come on, it's Maclaurin. All right, so our f of 0 is 1, so we're starting with 1, plus, then our next derivative is 0 over 1 factorial. I don't really have to write that, so we'll just write it like that, times x, plus, actually it was negative 0, wasn't it? Yes, it was. And then our next one is a negative 1 over 2 factorial times x squared. And then we have ourselves plus a 0 over 3 factorial. That's this 0 right about here. X to the third plus, and then we've got, this is the fourth one, we've got 1 over 4 factorial, x to the fourth. And okay, so maybe I get rid of all these 0 terms here. F of x is equal to, it's starting with 1 here, the 0x is gone, and then I'm going to rewrite this one, the next term, as a negative x squared over 2 factorial. The x cubed one is gone, and then I'm going to have the x to the fourth positive x to the fourth over 4 factorial. Can you guess what the next term is going to be? It's alternating, so it's going to be minus. And then our next power is x to the sixth over 6 factorial plus, what's next? How about x to the 8th over 8 factorial? Okay, so now we need to establish a pattern here, and notice that our exponents here are all even numbers, and also notice that our factorials down at the bottom, they're the same thing. They're also even numbers. They're the same as the powers. Even numbers. Well, even numbers, even, we write that as 2 times n. Let's see if all of that works, that 2 times n thing, where this is supposed to be our 0th term in our first one and then our second one. So here, let's just try this n equals 2 right here. So if I plug 2 in here, 2 times 2 is 4. Yeah, that seems to work. Yep. And then, of course, I need to build my alternator in here. So what we've got going on for cosine x is equal to this series here from n equals 0 to infinity of, let's throw in an alternator. I'll start with n. Let's see if that makes sense. If I plug in a 0 power here, that's negative 1 to the 0. It's a positive 1, which is that, right? If I stick in a positive 1, that's negative 1 to the first power, negative 1. It's negative. That checks out, so that's good to go. And then we'll build our fraction as x to the 2n power over 2n factorial, right? Again, if I stick in a 0 here, stick in a 0, that's 2 times 0, it's 0, and we're saying the 0 factorial is 1, and that gives us our first term there. If I stick in a 1, 2 times 1, second power, this one is also to the negative 1, so we get that negative, and then 2 factorial, which is this thing. Everything seems to check out for sure. Hey, what's left to do? I believe it's at the interval of convergence, right? So we basically want to know what's the domain of this thing. Where does this actually converge to cosine? To find that out, we performed the ratio test. Why am I writing down the word ratio? I don't know. Here, let's just do the ratio test. Limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term. Negative 1 to the nth, x to the 2, and then I need an n plus 1 on it, over 2 and n plus 1, all of this factorial, right? And then we'll multiply by the reciprocal there, which is negative 1. No, it isn't. It's 2n factorial on the top, over negative 1 to the nth, and x to the 2n. And let's do some simplification. So distributing that 2, the power is 2n plus 2, which means that's exactly what this factorial is down here, 2n plus 2. And then we'll expand out that factorial so we can cancel some stuff. This is going to be a 2n plus 2 times, subtract 1 from it, 2n plus 1, subtract 1 more, 2n, there we go, factorial, and then it gets to cancel. And of course we can cancel the negative 1. Oh, you know what I forgot to do? Did anybody point it out? You probably did. I just didn't hear you. It's to the n plus 1th power. Not that it really matters because it's going to cancel. Anyway, subtract your exponents on the x here. So you got 2n plus 2 minus 2n. The two n's will cancel, leaving you with an x squared up top. So let's simplify stuff. Limit as n goes to infinity. Absolute value of x squared is the only thing that's left upstairs, and then downstairs we have the 2n plus 2 times 2n plus 1. We can take it out because it's even. You know how we do it. 2n plus 1. And the limit doesn't affect this guy. It stays constant. You can get rid of your absolute value if you really, really wanted to. Not that it matters because you know what? The value of this limit's just 0. Bottom's just getting bigger and bigger and bigger as the top stays the same. So 0, which is less than 1. And we know that that means that this thing converges for all real numbers. Negative infinity. That's an infinity symbol. Take my word for it. To infinity. And there you have it. There is the Maclaurin series for cosine. And it is one of those that you absolutely need to have memorized, because do you want to do this whole process right here on the AP Calculus exam? No, you just need to know cosine, just like you just need to know sine. Here, I've got a little something to show you here. Here is that thing that we just came up with, summation from n equals 0 to infinity of negative 1 to the nth power, and then you have your even powers. Hey, remember that cosine, it's an even function. Well, there you go. And here, let's take a look at some pictures of this thing. Of course, it's going to start with the 12th polynomial, but here you can still see it getting closer. The polynomial is getting closer as we add more and more of these terms. And of course, the Maclaurin series, the series, not the polynomial, would add an infinite number of these, and it would perfectly line up the whole entire function of cosine.